All right, so before we move on, I wanted to go over one more interesting application of the conservation of linear momentum, and that is to derive the rocket equation. Now, traditionally, the rocket equation requires calculus to solve, so what we're going to do is a slightly different version of it, okay? We're going to develop a set of recursive relations, which we'll be able to use to get some numbers for what the velocity of this rocket is after some time t, okay? And here's how we're going to do it. So we're going to have this kind of before and after picture, okay? So I'm going to let this be t equals 0, and I'll let this be t equals 1 second, okay? So initially, the rocket has not fired anything. It's just sitting. We'll say its velocity is 0. We'll make that relative to, say, the Earth, but I'm not going to put gravity in here. We'll assume that it's already very far away, but we're tracking it from Earth, okay? So in that case, the velocity v will be the speed of the rocket once it gets going, okay? But initially, its velocity is 0, right? So here we have that v is equal to 0. Also, I'm going to write this as v sub 0, meaning v at time 0, okay? This will be v at time 1, okay? And so our objective here is to figure out how can we calculate v at time 1, okay?
Okay.
So before, nothing has happened, but afterwards, we have fired our rockets. This has resulted in a change in mass of our rocket ship. Typically, rockets are about 80 to 90% fuel by mass, okay?
Okay.
So that would be a 10 to 20% payload weight, okay?
Okay.
So as we fire the rocket, it ejects the mass out the back, right? This is usually through a chemical process, right? There's an explosion that takes place in a chamber, and those fast-moving gas particles, right, from the ignition are directed out the back of the rocket. It's a little bit like sitting in a boat and throwing bricks out the back end. You'll observe that when you do, A, the boat gets lighter, right?
Yeah.
And B, the boat starts to move. It obtains some velocity, okay?
Okay.
Now, we're going to assume that because of the combustion process, the uniqueness of the combustion process, that the speed at which the gas particles are being ejected out the back, which we'll call exhaust, is a constant. We'll call that v sub ex, okay?
Okay.
But now relative to Earth, right, the speed of the exhaust particles will actually be v sub 1 minus v ex, okay?
Okay.
Because if the rocket is moving, then the exhaust particles will be moving as well, okay? And so we'll have to take the difference. It's just a relative frame of reference. We talked a little bit about frames of reference before. You know, if you're on a train car, you throw a ball at 5 meters per second. On the train car, the speed of it is 5 meters per second. But to someone on the ground, they're going to see it equal to 5 meters per second plus the speed of the train.
Okay.
Okay?
Yeah.
If I'm moving away from the person standing on the side of the tracks and I throw the ball backwards, so I throw it at minus 5 meters per second, right?
Yes.
Then you'll have to take the speed of the train minus the speed of the ball that I threw to see its relative velocity. So the speed of the gas particles relative to the Earth is the velocity of the rocket minus the velocity of the exhaust particles, okay? So now what we can do is we can set up a conservation of momentum situation, okay? Before, so P before, will just be equal to m0. Why do I call it m0? That's the mass of the rocket at time 0, okay?
Okay.
We haven't lost any, we haven't made any, haven't combusted anything yet, so we still have all the fuel plus the payload, right? So this will be the payload plus the fuel, okay?
Okay.
Times the velocity at time 0, okay? Which you might recall is 0. P after is going to be equal to the momentum of the rocket plus the momentum of the exhaust, okay? It's a little bit like a rifle recoil problem, right? If I shoot the rifle, the bullet will shoot out the end of the rifle, right?
Yeah.
But there's a recoil force, right, in the opposite direction, okay?
Okay.
Those forces are equal because they are interaction force pairs, right?
Yeah.
But the speeds aren't equal, right? The gases are coming out at a very high speed. The rocket is not moving at an equal speed, right? So we can calculate what these terms are, though. P of rocket is just going to be m1, because it's after, right? T equals 1, times v1, velocity of the rocket, plus the momentum of the exhaust. Well, that's going to be this term v1 minus v exhaust times this delta m. This delta m is the little bit of mass that I've combusted and shot out the back. So you can see it's represented here as this little piece of mass. It's flying out the back, okay?
Okay.
And it represents the change in the total mass of the rocket ship, okay?
Okay.
And so at this point, we'll need to observe, I'll write note, that M1 is equal to M naught, or M sub 0, minus delta M, okay?
Okay.
Because that's the new mass of the rocket. It's a little bit lighter than it was before, okay? So if I substitute that in for M1, I'll get M naught minus delta M times V1 plus V1 minus V exhaust times delta M, okay?
Okay.
Now I'm going to distribute these two terms and just do a little bit of algebra. So we'll get M naught V1 minus V1 delta M plus V1 delta M minus V exhaust delta M. Now notice that these two terms here are the same, and they cancel, right? And so all I'm left with in P after is M naught V1 minus V exhaust delta M. Conservation of linear momentum says that P before is equal to P after, which says that M naught V naught is equal to M naught V1 minus V exhaust delta M. Okay?
Okay.
Now what I want to do is I want to solve for V1. That's the unknown quantity, right? That's the unknown velocity we don't have yet, right? So let's solve for V1. And what we'll find, after dividing out M naught and moving the exhaust velocity over to the other side, we'll have V naught plus V exhaust times delta M over M sub 0. Okay?
Okay.
That's for one time step, right? That's going from t equals 0 to t equals 1. We can generalize this for any time step, okay? So I'll say for the nth time step in general, V sub n, the nth time step, is equal to the previous time step, the n minus 1 time step, plus the exhaust velocity times delta M divided by M, the previous mass, M sub n minus 1. So any questions on what we've done so far? It's pretty straightforward, right? We just calculated the momentum before, which was just M naught V naught, right?
Yes.
And then the momentum after, which is the momentum of the rocket plus the momentum of the exhaust. Okay?
All right.
Probably the funniest bit of business that we've done here is that we've written the velocity of the exhaust as a relative velocity with reference to an inertial reference frame like the Earth. Okay?
Okay.
So we have to subtract the exhaust velocity from whatever velocity the rocket may have at that moment. Okay?
Okay. And what do you mean by in general?
Oh, well, so here I did it for one time step, right? So what I'm saying now is that we could keep doing this, right? We could then calculate V sub 2, and we find that it was equal to V sub 1 plus V exhaust times delta M over M1.
All right.
Okay? And we could keep going in that fashion, which means that for any time step, right, the velocity will be equal to the previous time step's velocity plus this term right here. Okay?
Okay.
Does that make sense?
Yes.
Okay. So now let's put it to practice. Let's actually calculate some stuff with it. So I'm just going to erase these equations here. Maybe I'll write the result up here. That V sub n is equal to V sub n minus 1 plus V exhaust delta M over M of n minus 1. Well, remember, these subscripts tell me what time step I'm on. Okay, so I've discretized the time steps. This would be a very good way to do it if you were going to do it by computer, for example, and simulate this stuff on a computer. You could even put this into a spreadsheet and calculate these velocities. Okay? You'd have to do it recursively. You'd have to calculate the first time step, and from that calculate the second velocity, right, in the second time step, so on and so forth. That's what we're going to do here. We're going to make a table. So we'll say T, M, and V. Okay? So time T equals 0, the mass, and we'll set some, well, use some parameters here. Let's let the mass be equal to 100 kilograms. Okay? Let's let delta M be equal to, I think, 10. That's what I did in my notes. 10 kilograms. Okay, so each time step, it's going to be combusting 10 kilograms of fuel. Okay?
Okay.
And, of course, the initial velocity will be 0, right? So V sub 0 will be 0. it's going to be handy to have this term, right? This v sub ex times delta m, right? That's going to be 100 times 10. Oh, I didn't specify the exhaust velocity. I need to put that in here. The exhaust velocity is going to be equal to 1,000 meters per second, okay?
Okay.
So 1,000 meters per second. So the exhaust velocity times the change in mass will be 1,000 times 10. That's 10,000, and that'll be kilogram meters per second, okay?
Okay.
Don't worry about the units because we're going to use this in this recursive formula. So initially the mass is 100 kilograms, right? And the velocity is 0. So that's the 0th time step when we just start out, right? The initial condition. At the first time step, what is the mass going to be? Well, remember, the mass for the nth time step is equal to the mass for the n minus 1 time step minus the delta m, right? Whatever we're subtracting off of it, right? So each time step we're subtracting from the total mass of the rocket
Yeah.
this delta m, right? It's at 10 kilograms. So in the mass at time t equals 1 of the rocket will be 90 kilograms, okay?
Okay.
What's the speed of the rocket? Well, our formula says that it's the previous speed, which is 0, plus this velocity of the exhaust times delta m, which is 10,000, right? Divided by the mass from the previous time step. Well, the mass from the previous time step was 100, right? And so that is going to be equal to 10,000 divided by 100. That's going to be equal to 100 meters per second, okay?
Okay.
In the second time step, the mass will decrease to 80. I'm just subtracting 10 kilograms off each time I take a time step, right? So at t equals 2, that's the second time step, our mass goes down to 80 kilograms. What's our speed going to be this time? Well, it's not 0, right? It's the previous velocity, which was 100 meters per second, plus this 10,000 again, right? That's that velocity, the exhaust velocity times the change in mass, divided by the old mass, which is 90, right? And so this comes out to be approximately, I think it's 211 meters per second, okay? In the third time step, the mass will be 70 kilograms. The velocity will be the 211 meters per second from the previous time step, plus 10,000 divided by 80, which is going to be approximately 336 meters per second. In the fourth time step, we'll have a mass of 60 kilograms, and our new velocity will be 336 meters per second plus 10,000 divided by 70, which is approximately 479 meters per second, okay? Now I'm just going to keep filling these values in. This will be 50, and this will turn out to be 646 meters per second. In the sixth time step, this will be 40, making this 846 meters per second. In the seventh time step, we'll have a mass of 30, and we'll have a speed of 1,096 meters per second. And in the eighth time step, we'll have a mass of 20, and that'll give us a speed of 1,429 meters per second. And then in the ninth time step, we'll have a mass of 10 kilograms, and our speed will be 1,929 meters per second. Now, I'm going to assume that our rocket ship was a 10% payload rocket, and so we're out of fuel. Okay? All we have is the 10 kilograms of payload, right?
Yeah.
Left. Okay? Now, if we plot these values, what does it look like? Well, we're going to go up to roughly about 2,000 up here, right? So 2,000 meters per second for our velocity, right? Which means that about halfway we'll be at 1,000 meters per second. As far as time goes, we'll say if this is, roughly 10 seconds, we'll make this 5 seconds. So we've got some point. At 9 seconds, right, so about here, we're almost 2,000 meters per second in our velocity. So we'll put that here, okay? For our, at 5 seconds, where were we? At 646, so this would be 500, so maybe somewhere around here, right? And we can, at 0, of course, we're at 0. And if I just kind of interpolate these points, it's going to look something like this. So I'll just move that to fit my graph. Okay? So this is the function that we get for our velocity. Okay?
Okay.
Okay, so this gives us the velocity of the rocket as a function of time. Okay? You can see this getting faster and faster and faster and faster, right?
Yeah.
Up to burnout, at which point it's just going to continue traveling on at that constant velocity, right? because we're assuming it's in space or something, right? So now that we've seen an example of this calculated, right? And of course, you could write a computer simulation that could do this. You could put in more realistic parameters. You could take far more time steps, okay?
Okay.
You could even add in the effects of gravity and stuff like that. Now I want to look at this rocket equation just a little bit more. If I take this, notice that delta V, right, is equal to V sub n minus V sub n minus 1, right?
Yeah.
So if I just subtract V sub n minus 1 from both sides, I'll get that this is delta V equals exhaust velocity times delta m over m sub n minus 1, which I'm just going to call m for now, okay? That's just the current mass of the rocket at some time t, right? Like I could put in as a function of t if I wanted to. If I divide both sides by delta t, right, I'll get delta v over delta t equals exhaust velocity times delta m over delta t times 1 over the mass as a function of time. Yes?
Yes.
Multiply both sides by the mass, and I'll get the mass as a function of time. What is delta v, delta t, by the way? What is that quantity called? The change in velocity divided by duration is?
Acceleration.
Acceleration, right? So this is my acceleration, right? I'm just going to write this as m, right, so that we're not confused. This will be equal then to v e sub x delta m over delta t. Where delta m, delta t, that's your fuel burn rate, right? How much mass per unit time am I burning fuel, right?
Yes.
If I multiply that times the exhaust velocity, it turns this into the thrust, right? Which is a force, okay?
Okay.
Mass times acceleration, that's a force, right? So we can see this as well, this is Newton's law now, right? Saying that the sum of the forces, in which case we only had one, the thrust, right, is equal to the mass times the acceleration, right?
Yeah.
And of course we're allowing the mass to be a function of time as well, as is the acceleration. So it's a little more complicated. I'm not going to get into the details of that. But this is the thrust. So let's do a quick calculation for some thrust. Before, what was our example? Now I want to do a different example. Let's say we have a burn rate, a fuel burn rate, delta m over delta t, is equal to 200 kilograms per second. Right? That's a lot of mass. Every second you're burning 200 kilograms of fuel, right? How much thrust are you going to produce? That's what I want to figure out. Well, kind of a typical exhaust velocity might be 2 kilometers per second. That's 2,000 meters per second, right? So I can calculate the thrust. We'll call it F. Thrust will be equal to 2,000 meters per second times this 200 kilograms per second. That is going to give me 4 times 10 to the 5 newtons, okay, which is approximately, it's about 90,000 pounds of thrust, okay? For comparison, the Saturn V rocket, which took our astronauts to the moon at liftoff, had a thrust of about, I think it was 7.5 million pounds of thrust. So quite a bit more than this toy rocket that I've shown you here. Right, the last thing I want to mention is that had we had calculus at our disposal, right, we would have done things differently, right? We wouldn't have generated this recursion relation, or recursive relation, to calculate the velocity for the rocket. Instead, we would have set up what's called a differential equation, right? We would have used calculus to solve this thing, and we would have found that the rocket equation says the final velocity is equal to the initial velocity plus the exhaust velocity times the natural logarithm of the initial mass divided by the final mass. So here, this would be just to calculate what is the final velocity of the rocket at burnout, right?
Okay.
So it's going to equal to the initial velocity plus the exhaust velocity times the natural logarithm of the ratio of the initial mass to the final mass, okay? So using our 90,000 pound thrust example from before, if we said that the initial mass of the rocket was 20,000 kilograms, okay? And of course that its initial velocity was 0. And let's assume that we have a 20% payload, right? Then the final velocity of the rocket will be equal to, and remember in our previous example we had an exhaust velocity of 2 kilometers per second. So I'll have the 2 kilometers per second. I didn't put in the 0 initial velocity, but it's there. Times the natural logarithm of the initial mass, which was 20,000 kilograms, right? Over the final mass, which is going to be 4,000 kilograms, And that will be equal to 2 times the natural logarithm of 5, which is approximately 3.77 kilometers per second. Okay?
Okay.
So pretty quick, right? If you're moving a few kilometers, that's almost 4 kilometers a second, right? Can you imagine going at like roughly 2 miles per second? That's a pretty quick clip, okay? Might leave it as a homework problem to figure out the Saturn V, if you assume a constant thrust, which of course wouldn't be the case, what its final speed would be. That might be a problem I give you for the homework.
Okay.
Okay, that's all I wanted to say about the rocket equation, but it's a neat example of the application of conservation of linear momentum, right, to solve a problem. And if we did the calculus approach to it, we would have also used conservation of linear momentum. We'd have just done it a little bit differently. But we get essentially the same result. And the graph I showed you, right, you will get the same thing, right, provided you take a small enough time step. Our solution will approximate the true analytical solution that you would have gotten from calculus. Okay?
Okay.
All right, that's it.